This is joint work with Shyam Narayanan. So first, I'll talk a little bit about trace reconstruction for linear strings, which is the standard trace reconstruction that has been studied before. So the setup is that we have an unknown binary string x of length n. It's going to be passed through a deletion channel, which deletes each bit of the string with some fixed probability q. The resulting bits are going to be concatenated into a trace. And that's what we see. So we want to reconstruct the original string from seeing a lot of independent traces. So the question is, how can we do this, and how many traces do we need to recover the string with high probability? So for example, let's say the unknown string is this string here, and let's say q is about a half. So it'll be passed through the deletion channel, and these bits marked in red will be deleted. And then what we see is the result of concatenating all of the remaining bits together. So we see 110, 110. And we want to determine what the original string is after seeing many different traces like this. So the motivation for this problem comes from some questions in computational biology studying DNA. So first, there's the multiple sequence alignment problem, where given DNA sequences from lots of descendants, you want to determine the sequence of the ancestor. And there's also the question of DNA storage, where DNA data is stored in some DNA, and we can read the data by sequencing, though this is somewhat noisy, and for example, some bits might be deleted in the process. So some previous results in trace reconstruction for linear strings. So for worst case reconstruction, by which we mean we want to be able to reconstruct any arbitrary string of length n. So first we have Holenstein et al. Showed that we can do this in e to the roughly square root of n traces. Then simultaneously, Nazarov and Perez and Day, O'Donnell, and Servadio improved this to e to the roughly cube root of n. And very recently, Chase improved this to e to the roughly n to the 1/5. There's also the case of average case reconstruction, in which the unknown string x is randomly chosen uniformly at random from all length n strings. And in this case, Holenstein et al. Showed that if the deletion probability is small enough, we can do this in polynomially many traces. This was improved by Perez and Zhai to e to the roughly square root of log n if the deletion probability is less than a half. And Holden, Pimentel, and Perez showed that for all deletion probabilities, we can do this in e to the roughly cube root of log n. Finally, there's the question of lower bounds. So how many traces are required for both worst case reconstruction and average case reconstruction? Holden and Leon showed that you need at least n to the 5/4 for worst case and log n to the 9/4 for average case. And this was improved by Chase to n to the 3/2 and log n to the 5/2. So the new variant that we introduce is circular trace reconstruction. And it's essentially the same, except instead of linear binary strings, we have cyclic binary strings or circular binary strings of length n, and we're passing them through a deletion channel probability q, and the results are concatenated, the remaining bits are concatenated into smaller circular strings, and we want to reconstruct the original string up to cyclic rotation. So equivalently, it's linear trace reconstruction, except the string will undergo a random cyclic rotation before entering the deletion channel. So we can just pick an arbitrary point in the circle to start the string. So for example, let's say we have this linear string on the left. It'll pass through the deletion channel, and all the bits marked in red will be deleted. The resulting bits are concatenated into the smaller circular string, and we can read it as a linear string by choosing an arbitrary bit to start the string at. So the question is, can we achieve similar bounds on the sample complexity compared to linear trace reconstruction? So now I'm going to talk a little bit about our results. So first, for worst case circular trace reconstruction, where we have some arbitrary unknown circular string X, and it's going to go through a deletion channel probability Q, then with high probability, we can recover X using e to the roughly n, a cube root of n independent traces up to log factors in the exponent, provided that n is the product of at most 2 primes. So n is prime, it's the square of a prime, or is the product of 2 different primes. And the reason for this dependence on the prime factorization of n is that a certain part of our algorithm relies on a number theoretic condition that only holds for these n. There's also, we also have results in average case circular trace reconstruction where we have a random circular string X of length n that goes through some constant probability deletion channel. And in this case, we can recover X using polynomially many traces, though the exponent will depend on the deletion probability Q. Finally, we have a lower bound for worst case circular trace reconstruction, where we show that up to log factors, we need at least n cubed independent traces to recover the string with high probability. So this is higher compared to the n to the 3 halves known for linear strings. So now I'll sort of go through our proofs. So for worst case reconstruction, we have, again, an arbitrary unknown circular string X of length n. It goes through a deletion channel of probability Q. And as long as n is the product of at most 2 primes, then we can, with high probability, determine what the original unknown string was using e to the O of n to the 1/3 traces up to log factors in the exponent. So the main idea of our algorithm is that we want to construct a certain polynomial q of z of x, q of zx, where it's a polynomial in z that depends on x. And we want to find an unbiased estimator for this polynomial that we can compute just based on the traces of x. And essentially, the idea is that we want to answer the question of whether traces we see are coming from some string x or some string y. So in order to do this, we first need that this polynomial q is not too large a magnitude for the values of z that we're plugging in. And we need that q of zx and q of zy differ significantly for some z if x and y are different. So the idea is that we can use our unbiased estimator to estimate we can take the average of the values we see from evaluating the unbiased estimator and see if they're closer to qzx or qzy. And if x is the original string, then with high probability, it will be much closer to qzx than qzy. And if we run this through all pairs of strings, then we'll see that x will win in every pair, and then with high probability, x will be the string. We can conclude that x is the original string. So this is essentially the same argument used for linear trace reconstruction, except we need to come up with some different polynomial q to handle circular strings. So in particular, this q should be invariant up to cyclic permutations in x. And the reason we can't handle n with too many prime factors is that in order to encode the circular string condition, we need to use nth roots of unity in our construction. And these nth roots of unity are less well behaved for n with too many prime factors, and we need certain arithmetic properties from these roots of unity for our algorithm. So for the unbiased estimator, first let me define the polynomial q. So for linear strings y, we can define this polynomial pzy, where we just write the bits into the coefficients. So it'll be a degree n polynomial where the coefficients are y1 through yn. And then for every circular string x, we define qzx to be the sum of this expression over all rotations y of x, by which we mean start from the linear strings resulting from starting from each bit in x. And so we're summing z to the 2n times p of zy squared times t of 1 over z squared y over all rotations y of x. Notably, when z is an nth root of unity, every term in this sum is equal. And the way to see this is that to note that because if z is an nth root of unity, if you shift y over by 1 bit, then p of zy squared will multiply by z squared, and p of 1 over z squared y will divide by z squared. So the expression remains unchanged. And so we can show that there exists a function h of a trace of that takes a trace of x and z, such that the expectation of this overall traces is equal to qzx. So this is what allows us to estimate qzx given many traces of x. And so this is our unbiased estimator, and in order to use this, we need certain bounds on q and h. So first, we need that h is bounded in magnitude, so we can apply a Chernoff bound. So we have that we'll be using z on the unit circle close to 1. So depending on a parameter L, we'll have z vary along the arc of the unit circle near 1 of length 1 over L. And we have this bound on h in terms of L. We also want, if x and y are different strings, for q of zx and q of zy to be far apart. And so we have this result where as long as qzx and qzy are different as polynomials, then for some z along this arc, they will be sufficiently far apart for us to distinguish x and y. And this is essentially just a Chernoff bound. And once we have enough traces with high probability, if x is the correct string, then the average overall evaluations of h will be much closer to q of zx than q of zy. Now the issue here is whether qzx and qzy are different as polynomials. So again, we define pzy and qzx for linear strings y and circular strings x. So qzx, because we're summing over all rotations of x, if we cyclically shift x, then this qzx remains unchanged. But there's a possibility that for different cyclic strings, x and x prime, qzx and qzx prime turn out to be the same because we're summing over all rotations. So the question is, when can we distinguish between different circular strings x and y using qzx? And so using some, after some computations in the cyclotomic field of the nth root of unity, we can reduce this. So first, note that by what we said before, for root of unity z, every term in the sum is equal. So to demonstrate that qzx and qzy are not equal as polynomials, we just need to show that for some root of unity z, they're not equal. Hence, for some root of unity z, the individual term p of z squared times p of 1 over z squared, these terms are not equal. So we want this to be true if these two terms are equal for x and y. For all nth roots of unity z, then x and y are rotations. And after some computations in the cyclotomic field, this can we can show that this follows from the simpler condition, which is that whenever the ratio pzx to pzy is an nth root of unity for all roots of unity z, then x and y are rotations of each other. So it's easy to see that the converse of this always holds. So if x and y are shifted, if y is a shift of x by k positions, then this ratio will always just be z to the k. But this statement only holds, this statement is true if and only if n has n most 2 prime factors. So when n has more than 2 prime factors, there's a counterexample that shows that for different circular strings, you can get the same result. So this algorithm won't work for those values of n. Okay, so to summarize the algorithm, let's say we have some unknown arbitrary circular string of length n, x, and n is the product of at most 2 primes. So then we're going to be testing every pair of distinct circular strings of whether it's more likely of that the traces are coming from y1 or y2. And to do this, we consider qzy1 and qzy2. And so because n is the product of at most 2 primes, the two polynomials are different. And so for this certain choice of the parameter L, we can look at the arc on the unit circle and we can find some z along that arc such that qzy1 and qzy2 differ by a large enough amount. And then we can average our unbiased estimator over all the traces of the unknown string. And we can look at if the average is closer to qzy1 or qzy2. And with high probability, the correct string x is going to win every pair it's in. So there's going to be some unique string x that wins in every pair it's in, and we just return that string as the answer. And so because h is bounded, we can apply a Chernoff bound and union bound over all pairs to show that this will succeed with high probability. So this gives the result. And so we were only concerned here with the sample complexity. So this algorithm here is horribly inefficient. There are techniques for doing this reconstruction more efficiently using some linear programming. And this has been done already for linear trace reconstruction. So now for the average case, we have an unknown randomly chosen circular string of length n and some constant deletion probability q. We pass the string through the channel. And we want, so we can determine with high probability what the string was using polynomially many traces where the exponent is some constant depending on the deletion probability q. So by random, we're going to assume that we can sample x using this process where we take a random string, random linear string, and we just apply a random rotation, or we just like wrap it around. And while this distribution is not quite uniform on all possible circular strings, it's close enough, and our arguments are easily modified to work for that case as well. So for the ease of presentation, we're going to assume that this is how we're sampling x. So the main idea is to let k be some integer that's on the order of log n, and we're going to use the traces to recover what is called the k-dec of x. So this is the multi-set of length k consecutive substrings of x. So we're going to use a similar argument to the worst case reconstruction where we're just going to test all pairs of k-decs and see whether the traces are coming from one or the other. And to do this, we're going to use some string s of length k that appears a different number of times in the two k-decs. And we're just going to check to see how often that string is appearing in the traces. So this idea was also independently found by Chen et al. In a recent paper on a different variant of trace reconstruction as well. And then once we have the k-dec, we can show that with high probability, a random circular string is going to be uniquely determined by its k-dec. So we're just going to use the traces to get the k-dec, and then we can recover with high probability the string from the k-dec. And a string is going to be uniquely determined by its k-dec when when all the elements in its k-dec are distinct. So we're going to say such strings are regular. So we're going to require that all length k consecutive substrings and length k minus 1 consecutive substrings are pairwise distinct. So then once we have the k-dec, we can glue together the k-dec back into the original string x. And the way this works is we take an arbitrary element of the k-dec and we look at the last k minus 1 bits of this string. And there is a unique string in the k-dec that begins with these k minus 1 elements. So we can glue these two strings together and we can sort of just keep on going until we recover the whole string. So the probability that a string is regular is going to be is going to tend to 1, provided we have a high enough constant factor in front of the log n. So the probability that any 2 given length k substrings are equal is 1 over 2 to the k, and we have O of n squared possible pairs where they can fail, so we can union bound over all of those pairs. And this gives a failure probability of O of n squared over 2 to the k, which we can make small enough by just taking k to be c log n, where c is sufficiently large. So now, as mentioned before, we want to distinguish between whether our traces are coming from a string with kdec s or a string with kdec t. So let's say those x and y are strings with kdecs s and t. So what we're going to do is we're going to take some string s of length k that appears in s and t a different number of times. So in other words, s appears contiguously in x and y a different number of times. So if the probability that a random trace of x, we're going to compare the probabilities that a trace of x starts with x and a trace of y starts with s. So because s appears a different number of times in x and y, we can expect that these probabilities will be somewhat far apart. And once we know that they're far apart, we can just look at our traces and see at what rate they're starting with s. And that'll tell us whether it's more likely that the traces are coming from x or y, or have kdecs coming from a string with kdecs s or t. So now we just want to bound the probabilities that traces of x and y start with s away from each other. And the way we can do this is by an explicit expression for the probability. So we have this sort of combinatorial sum over all subsequences of the string that, when concatenated together, form s. So for x, let's say that c sub I is the number of occurrences of s as a substring of x, where as a subsequence of x, where the subsequence can be covered by a substring of length k plus I. So the probability that this subsequence appears at the beginning of our trace is given by, first, we want 1 minus q to the k for the probability that the subsequence is preserved, and then q to the I for the probability that the rest of the bits are deleted. And then we sum this over all I. And we also divide by n because we choose a random starting point for seeing the trace as a linear string. So this is well approximated by if we just so we have the sum here for all I from like 1 to n, 0 to n, so 0 to n minus k. So we can cut this off at we can cut off the terms where I is bigger than much bigger than k, because then q to the I will make those terms small enough where it's essentially negligible. So now we have this expression 1 over n times 1 minus q to the k times this polynomial p of xs, depending only on x and s. And evaluating this at q gives us a good approximation for the probability that a trace from x starts with s. And we can do the exact same thing for y and find this polynomial p of ys. And as long as p of xs and p of ys evaluated at q are far apart from each other, then by a Chernoff bound, we can figure out if our traces are coming from x or y. So if, but there is the issue where p of x s of q and p of y s of q can be close to each other. And in this case, what we can do is we can simulate higher deletion probabilities by essentially feeding the traces through another deletion channel, this time with probability q prime minus q over 1 minus q. So the overall effect is that the string goes through a deletion channel of probability q prime. Then we just need that p of xs and p of ys differ by a large enough amount on this interval, say from q to q plus 1 over 2. And so this is true by a result of Borwin et al. And where we apply this result because we can apply this result because, first of all, the coefficients of P of xs minus P of ys are bounded in magnitude. So this is because C sub I is at most K plus I choose K, because there's at most that many possible subsequences times n. And so those coefficients are small enough because we restrict to I is O of K. And also the constant term of P of xs and minus P of ys is bounded away from 0. And this is because the constant term is just given by the number of consecutive occurrences of s in x and y. So this is C sub 0. And we assumed in the beginning that they were different. That's how we chose s. So because the coefficients of this polynomial are bounded and the constant term is sufficiently far from 0, it can't be very close to 0 on this entire interval, and that gives us the result. So to quickly summarize the algorithm, let's say we have an unknown random circular string x. We're going to let k be some constant times log n, and we're just going to check every pair of circular strings with different k to x. And we're going to compare qy1s and qy2 of s over the interval q plus 1 over 2, where s is some string that appears a different number of times in y1 and y2. And then we're going to simulate this higher deletion probability, and we're going to check how often the traces we see start with s. And just like in the worst case reconstruction algorithm, with high probability, the correct deck will win every pair it's in. And so with high probability, we can glue the deck back together into a circular string, and that's the answer. So the dependence of the constant CQ and the exponent on Q is, we can take it to be O of 1 over 1 minus Q. And again, this we only cared about the sample complexity, and this algorithm is very inefficient, but there are ways of making this more efficient using linear programming. And Chen et al. Cover a very similar case in their application of this technique. So now I'm going to talk a little bit about the lower bound, where for worst case circular trace reconstruction, we need at least up to log factors and cube traces. So the idea behind this one is the same as for linear strings. So we want to find two strings that are hard to distinguish just from their traces. And so the strings we'll take are x, which is 1 followed by n zeros, followed by 1 followed by n plus 1 zeros, followed by 1 followed by n plus 2 zeros. And so this is going to be some circular string where the ones are roughly evenly spaced around the circle. And we're going to take y to be its mirror image. So these are not the same circular strings, but we can't distinguish them in less than O of n over log n cube traces. And to get a bound like this, we essentially want to bound the distance between the distribution on possible traces for x and y. And by some focal results about the Hellinger distance, this will give us the desired n cube bound. And to work with the distributions, we first note that if we condition on a 1 being deleted in the channel, then the resulting traces of x and y have the same distribution. And otherwise, we just need to compute the probability that we see 1 followed by a zeros, followed by 1 followed by b zeros, followed by 1 followed by c zeros. And this is a relatively straightforward computation and bounding. Finally, I want to talk a little bit about future directions for circular trace reconstruction. So a lot of open questions remain. For example, there's the very recent improvement of worst case linear trace reconstruction to e to the roughly n to the 1/5. So the question is, can we match this for circular trace reconstruction, even for say n prime? Along that line, can we remove the dependency on the prime factorization of n in the e to the n to the 1/3 upper bound we have? Can we get a sub-polynomial upper bound for the average case, similar to how the linear average case is currently sub-polynomial? And can we improve the lower bound beyond NQ, maybe even to a super polynomial bound? Finally, we only consider the regime where the deletion probability is constant. And perhaps we can achieve better results if the deletion probability tends to 0 as n tends to infinity. Thanks for listening, and I hope to see you at the conference.